All right, we're gonna get started. Please find your seats. I need to do this as well. All right, good morning. So on the final lab, this is Dinrg, Decentralized Internet Infrastructure. Thanks for coming. It's my co-chair, Melinda Shore. I'm Dirk Kutscher. So Dinrg is a proposed research group in the IETF. So we have been meeting for a couple of times, so have been, trying to think about the good scope, try to figure out what are the communities that could work on this topic. And so this is basically our third meeting as a proposed research group. So I think we have a pretty cool agenda, and you probably have seen some discussion on the scope or charter on the mail list. Thanks for everyone who contributed to that. So we're going to come back to this at the end of the session. So if you want to spend some thoughts, maybe if you have some additional feedback or ideas on that discussion, please start thinking about it. Quickly, we have an IPR policy in the IETF. So essentially, please let us know quickly if you see IPR in this room that you are aware of, or that if you present something that is connected to IPR. Quickly, our group infrastructure. So we have a mailing list. Please join that if you haven't done so yet. We have a wiki where we kind of try to manage additional documents and point us to previous meetings and so on. The IETF data tracker. So once we are like a established group, also has all of that. Fortunately, we already have a note taker, so thanks a lot, Marie-José. She's doing it for us. It's super helpful. So sometimes we use the Etherpad tool here, but feel free to use what you like. Quick overview of the agenda. So we have 2 hours today. And we will start with an update on the Stellar protocol and a presentation on a formal verification approach. And then we talk about distributed authenticated mapping, so something we also talked about before. Sheha Bano is joining from London remotely, so it's going to talk about her coconut project. Tönnes is giving us some perspectives how Dinrg could relate or relates to what the Anima working group in the IETF has been doing. And then we have Bingyang Liu talking about their work on decentralized trustworthy internet infrastructure. We kind of, as I said, we left some time at the beginning to allow for some discussion on scope, next steps, feedback from you perhaps. So let's try to make this happen. All right, is there anything we need to do on the agenda? Any bashing, changes? All right. Good. With that, David. Okay. Yes, but you have to really be close. Be closer. Oh no, it's maybe not working.
How about now?
Better.
Okay, great. Okay, so I'm going to update you guys on the Stellar consensus protocol draft. I'll point out a couple of things that are new, but like the main new thing is like, the last meeting, the draft was almost unreadable, and now it's to the point that there's, like people are actually implementing it and like emailing me questions, but questions where it's like obviously they're understanding most of it, and there's like some ambiguities that need to be worked out. So if you tried to read version 0 and couldn't make heads or tail of it, now might be a good time to try again. Okay, so quickly by way of motivation, the goal here is to have some kind of like internet level consensus where the internet can agree on something. Right now, why would you want this? There'll be other motivation in later talks, like in particular the distributed mapping talk, for which there's actually a draft now. But as an example, let's say you wanted to transact atomically across incompatible or mutually distrustful systems, right? Like maybe you want to do a transaction where you transfer a domain name to someone and they send you a payment on some completely different payment network that has nothing to do with the domain name registry, right? Well, what if kind of like the internet was maintaining this secure append-only log? You could kind of leverage that as a secure, reliable coordinator for a two-phase commit, and you could kind of cause transactions to commit across both these separate systems that don't necessarily know about each other in advance, right? Another example, which will come up in a later talk, is what if you want sort of irrevocable or temporarily irrevocable delegation, right? I create an email account for you on my system, and I want to now certify your email address in such a way that I can't later equivocate and I want to certify a public key for your email address, and I don't want to do it in such a way that I can't take that back and certify somebody else's key for the same email address later on. So again, could the internet somehow enforce these delegation rules? Yet another example would be to verify, to have kind of verified disclosure of information, right? So this comes up particularly in the case of firmware transparency, right? You would like to, for example, put out an IoT device and make sure that random hackers can't, load malicious firmware on there. And so one way to prevent that is to say, okay, you can only load firmware on these production devices once the firmware has been, disclosed a week in advance on some public log, and the firmware can refuse to update itself unless there's proof of that. And again, if the internet were maintaining this kind of transparency log, and you could trust the internet, then this would work, right? So all of these would be addressed if there was some public append-only log that were sort of agreed on by the whole internet, right? So the next question is, well, what is the internet? This might seem like kind of a funny question to be asking at an IETF meeting, right? Because we think of here we all work to put out our protocol specifications, and then we think of organizations like IANA and ICANN that dole out identifiers, and many of these have recursive delegation capabilities, and this is all well defined. But in practice, if say like, Google and Netflix and Amazon and Comcast all like move to some parallel IP network where they kind of reuse domain names and IP addresses for, like in a way that was completely incompatible with IANA, no one in the US, very few people would actually care, right? People would think, oh, well, the internet, that's the thing where I can go watch movies on Netflix and search on Google, right? And, most people haven't heard of IANA and don't really care what it is. Similarly, if you go in China, people would have a different idea. They would want to reach, maybe Baidu and WeChat and whatever. Most people in China can't even reach Google, right? But there's a hypothesis here, which is that all these notions of internet will sort of transitively converge, right? And the reason for that this hypothesis makes sense is that the internet has this kind of inherent brinksmanship built into it, right? Where it's a global network. It's not centrally governed. It's built out of these pairwise peering and transit relationships, and the penalty for going off and starting your own network that's completely disconnected from the internet is so high that it sort of forces the thing together, and it forces people to work things out such that there's transitivity. So the goal here is to leverage this kind of internet hypothesis, the idea that, transitively everyone can talk to everyone, even if there's not direct connectivity, to create a consensus protocol that basically, whose kind of trust mirrors this pairwise peering governance structure of the internet. And so the idea is that everyone who's participating in this consensus protocol is going to pick a set of nodes, a set of other participants that they think is kind of important enough to speak for the whole internet, right? So let's say, I think that, the internet is whatever contains like the IETF website and wiki and mailing list and Stanford, right? So those are the sites that I care about. Maybe you're from China, you think that the internet is wherever you can reach, Baidu, WeChat, and Alibaba, right? And, so famously, like if you're in China, you can't even reach Google. So that's just not even part of your internet experience, right? On the other hand, both Alibaba and Stanford depend critically on Google, right? Because, at Stanford, we do a lot of Google searches. Google hires a lot of our graduates. If you're Alibaba, you actually need your inventory to be indexed on Google, right? So even if your employees can't search on Google, you still need connectivity to Google, right? And so, so the idea is that as long as, since we're all kind of indirectly depending on Google, as long as Google is honest in this example, we want this consensus protocol to be safe. Now, of course, we might also want fault tolerance in case, Google's unavailable or some of Google's servers are unavailable. And so for that, you can say like pick multiple quorum slices and then say, any one of those kind of satisfies you that if everyone in that quorum slice agrees and everyone they think is important agrees, then you're kind of dealing with something that the whole internet can agree on, right? And, so for example, maybe an example of a multi-quorum slice configuration might be you depend on 4 out of the 5 FANG companies, right? Because these are big companies with, reputations to protect and big market caps. Or more realistically, maybe you depend on, for each FANG, they have multiple servers. So you depend on, it's kind of like 3/4 of the servers from each of the 5 FANGs, right? Okay. So once you have this notion of a quorum slice and individual people, think this quorum slice speaks for the internet, a quorum is simply the transitive closure over quorum slices, right? So quorum is a set of participants, that contains at least one quorum slice of each of its members. And the quorum also can't be has to contain at least one participant, obviously. Okay, so using this, SCP builds is basically a Byzantine agreement protocol that has open membership and kind of relies on this this decentralized decision about who's actually important and who should have market clout kind of in this in the internet. And here's kind of an example to illustrate this this example. I showed this last time, but in case there's anyone new or in case it's not fresh in your mind, here I'm visualizing quorum slices by drawing an arrow from a node to all the other nodes that node depends on, right? And so in this example, you can see that V1, sorry, V2, V3, V4 is a quorum because it's also a quorum slice for each of its members. V1, V2, V3 is a quorum slice for node V1, but it is not a quorum, right? V1 is saying, I'll agree to stuff if V2 and V3 do. V2 and V3 are saying, we'll agree to stuff if V4 does. So the smallest quorum, including V1 in this example, is the set of all nodes. And so that gives you kind of a sense for how this transitive property works. If I depend on just Stanford, but Stanford depends on a bunch of other people, then kind of, I'm not going to be forked from anybody. I'm not going to be forked from Stanford, but I'm not going to be forked from anyone Stanford considers important either. Okay, so the way we represent these quorum slices, of course, a quorum slice kind of mathematically can be an arbitrary set of nodes, including yourself. You have to be in every one of your quorum slices. But in practice, that would not be easy to represent compactly. And often if you want kind of like 3 out of 4 type and K out of N type configurations, you don't want to kind of enumerate every single quorum slice. So instead, in the protocol, we're saying that you describe your quorum slices kind of recursively as a K of N kind of thing, and each of the K or each of the N things can be either a particular node named by its public key, or it can also be another sort of K of N, and we let it recurse twice because that's recursing once is probably good enough for most cases, so twice should probably be good. At one point we let it recurse more, and then people pointed out that like a lot of RPC parsers use like language level recursion to kind of parse nested data structures, and so you can like blow out the stack in the implementation. So this will be less prone to kind of implementation issues. Okay, so that's how we represent a quorum slice. And every single message that's part of this protocol is now going to specify the sender's quorum slice as a SHA-256 hash of the serialized quorum slice data structures that I showed you on the previous message on the previous slide. So basically, the protocol is specified in XDR, since that's already an internet standard, and you can see that every message basically comes in an envelope where you have a statement and then a signature on that message, and the statement basically includes a node ID, which is a public key of the sender, a slot index because you're using SCP to agree on a series of slots at 5-second intervals. That's your log. Then the quorum set hash is the SHA-256 hash of the quorum slices. And then there's 4 different messages that I'll go through, and you can embed one of these in any given signed message, right? These are nominate, prepare, commit, and externalize. So the main subroutine that's used kind of over and over again in these messages is this thing called federated voting, which you can sort of maybe think of as a weird form of like Braca atomic broadcast, if you're familiar with the asynchronous protocols. Anyway, you sort of you use this protocol to decide between some statement A and potentially either decide on A, or maybe you want to be able to decide on A's opposite, which I'll call A bar here. So an A is a conceptual statement, and we'll plug various values of A in for the protocol. You start in this uncommitted state, and then you can vote for A, or you can vote against A if you think A is going to be false. And then if a quorum has all voted for A or accepted A, you progress to this other state called accepted. Then you have another kind of vote, kind of like a vote on the fact that the vote succeeded, a meta vote. And if you reach a quorum, again, of nodes that say they've accepted A, then you've confirmed A, and then the vote has succeeded. Conversely, you could vote for not A, you can then accept not A and confirm not A. Or if you voted for not A and you see a set of nodes that has all accepted A, they've accepted the opposite of what you voted for, and that set is big enough to intersect every single one of your quorum slices. So basically, that you'll never see a quorum that actually includes a voted A. Then you can move to accepted A. You can kind of change your mind, and well, even though I voted for not A, I'm actually going to accept A. But then to get to confirmed, you still need a quorum that accepts that. Right. And so the nice properties that you get from this here are that you cannot accept you will never accept contradictory statements so long as you have quorum intersection despite faulty nodes. In other words, even if you remove all the faulty nodes from people's quorum slices, there's still quorum intersection. And for that, we're now calling that property intertwined, that the nodes are intertwined. And also there has to actually be an honest quorum, right? Because otherwise you might not be able to do anything. And when you have both these properties hold, you're intertwined and you're in an honest quorum, then we call that intact. Right. So you won't accept contradictory statements if you're not intact. You won't confirm contradictory statements so long as you're intertwined. So even if you're not intact, you will, and you accept contradictory statements, you won't confirm those contradictory statements. Right. So during this voting process, you could get stuck. Right. There's no guarantee that you'll make it all the way to confirmed A, but if there's any intact node that actually confirms some statement, then there's a guarantee that all the intact nodes will confirm it, right? So once you've confirmed something, great. I can assume both for safety and liveness that all the other people I care about who are not compromised are actually going to accept this as well. Okay, so basically the outcomes you can get from federated voting are, the good outcome would be that the system is avalent, meaning like there's a quorum that's voted for A, and because you have quorum intersection, that means no other value will be agreed on by a quorum, and then everybody kind of realizes that a quorum did this, and so everyone can kind of agree on A as being true. However, if you have people voting against A, you might get a split vote, right? You can imagine a situation where neither A nor A bar gets a quorum because just the votes are split, and even if you're doing like a thin majority thing, you could have nodes failing so they don't vote, and so you just get stuck and you'll never actually finish, right? Or of course you could end up agreeing on A bar. Now, there's this other property though, that if you cannot vote against A, if the protocol does not admit a vote against for A bar, or if you can reason about the fact that a correct node will never vote against A bar, well then you will not get stuck, right? There's always hope that either people haven't voted or they voted for A. So if you, as long as there's a valid quorum, a non-faulty quorum, you can kind of convince enough people to vote for A who haven't voted yet, and eventually get a quorum, and eventually the system can agree on A. So if there's a statement that a kind of non-faulty node can't vote against, then we'll call that statement irrefutable. Okay. So with that background, I can now talk about how the protocol works, and basically applying this federated voting idea to a bunch of different statements. So the first phase of the protocol is you have to kind of decide what value to even try to reach agreement on in the first place, right? And so we call this the nomination phase. And so you start off in this nomination phase, and you're trying to grant these values. And a value is just an opaque string of bytes. From the point of view of the consensus protocol, you don't really care. You just care that there's some upcall to say, like, is this a well-formed value, so that you don't nominate or renominate a broken value. But basically, you're voting to nominate values, and there's no way to vote against nomination. You can vote to nominate a value. You cannot express an opinion on that particular value, but nomination is irrefutable, so it's not going to get stuck. And so what you do is you just run this federated voting subroutine that we just saw by starting for some values, and then when you see other people vote for values, you kind of echo their votes, and you also vote for things that you've seen other people nominate, as long as you think those are valid. And then once it reaches a quorum, or once you see a blocking set that's accepted it, you move the values from voted to accepted, and you keep going like this until you actually confirm at least one value nominated. Right, and at that point, you stop voting to nominate new values, right? So the nice thing is here that this protocol will actually converge on a set of values, right? Because at some, you're only going to vote for a finite number of values, and there's no way to vote against a value. It's irrefutable to nominate values. So eventually, you will confirm some value nominated. And at that point, the protocol will continue in the background. You may confirm other values, but at some point it will stop and converge on some set of values, right? Basically one problem in the last draft is I never said kind of like when you could stop the nomination protocol. And so we made some changes so that you have to keep sending your nominate messages until such point as there's a ballot that's confirmed prepared. And I'll talk about what that means when we get to the prepare phase of the protocol. Right, but at that point, once you've confirmed some ballot prepared, you don't care about the nomination value. Until then, the nomination value is how you try to get a ballot prepared. It's the value that you choose. Okay, so kind of here's the nomination flow, right? You kind of echo these nominations. Eventually everybody stops nominating new values because they've seen at least one value nominated, confirmed nominated, and then kind of the rest trickle around in the background until they converge on this set of values. And then you just deterministically combine those values, again, in an application-specific way. But if we were doing transactions, it could be like the union of the set of transactions. And this thing is guaranteed to converge. The only catch is you don't know when it's converged, right? There's this famous FLP impossibility result, which says you can't get consensus in an asynchronous system with a deterministic protocol. And so because of that, if this protocol, if you knew the protocol were done and had converged, you'd violate that impossibility result. It would mean this protocol doesn't work. So we have this thing you can kind of guess that this is probably converged, but we have to do something else to actually make sure that we're safe and we all agree on the same value. And that second part of the protocol is the balloting. Okay, so what is a ballot? A ballot is just a pair where you have a counter and a value. The counter is just an integer, and the value is kind of a candidate that you would output from the consensus protocol for a particular slot in your log. The ballots are totally ordered, where the counter is more significant than the value. And there's two kinds of statements that you can vote on for a particular ballot: commit and abort, where they're contradictory. Like abort means not commit. So you can only vote for a given ballot. You can only vote for either commit or abort, not both. And there's this very important predicate, which is called prepared. And to say that a ballot B is prepared is the same thing as saying that all of these abort statements are hold, namely abort B prime for every ballot B prime that's less than B, and for which B prime's value is not equal to B's value, right? And so this is very important invariant in the protocol, which is you cannot vote to commit some ballot B unless the federated voting has first confirmed every statement in the set prepared B. And this has an effect that, among other things, all of any votes that get stuck and any ballots that actually get confirmed committed will have the same value. Right, so this allows us to kind of continue to ensure that we don't get stuck, because we've kind of like split our votes on ballots containing two different values, and now we'll never know which of these values is the right one to put in this log slot. Instead, we'll just if both votes got stuck, then they had to have the same value. So then you can just vote to commit a higher numbered ballot that has the same value in it. Okay. So we start off the balloting with a prepare phase, and this is what the prepare phase contains. It contains a ballot, two optional ballots called prepared and prepared prime, and then these two counters, H counter and C counter. And what does this actually mean? Well, we can kind of translate this into federated voting messages. At its core, this is a vote to prepare ballot. Right, but it could be that you've also accepted ballot. You voted against it, but then you changed your mind and accepted it. So, but basically, if for ballot, this means you're either voting for ballot or you're accepting that this ballot is prepared. Right, meaning everything less than it with a different value has been confirmed, has been aborted, or you're voting to abort everything less than it. Then you've got these two optional ballots, prepared and prepared prime. If they are null, it means that you've actually accepted them as prepared, not just voting for prepared, but you've actually accepted for them as prepared. So a slightly stronger statement than what you're saying about the ballot. And the reason there are two of these is because if you remember the way I defined prepared, it says that everything less than the ballot with an incompatible value, with a different value, has been aborted, right? So all you need is the top two prepared things that you've accepted as prepared with different values to kind of fully define everything you've ever accepted as aborted, right? Because you've accepted as aborted all ballots less than prepared prime, and all ballots between prepared prime and prepared, except those that have the same value as prepared. And then if H counter is not 0, that means you're actually confirming this prepare of H counter and the ballot's value. And you don't you don't strictly need to tell people that you've confirmed something as prepared, but it's actually useful because it lets you kind of prune the quorum slices. Like if someone tells you they've confirmed something, that means that you can kind of not check their quorum slices when you're doing your quorum check to see if something actually constitutes a quorum, because they've already checked that one of their slices satisfies this recursively. And then there's a C counter, which when it's non-zero means you're actually voting to commit some ballots, basically everything between C counter and H counter. So C counter is kind of like the lowest ballot that you're voting to commit, and H counter is the counter of the highest ballot you're trying to commit. And once this commit phase actually succeeds and you've accepted a ballot as committed for any ballot, then you move on to the next phase, which is the commit phase, right? So this is just a little bit about, how am I on time?
Not good.
Not good. Okay, so I'll skip this. So then we've got some, like, not good meaning I'm over already. Okay, well, so then we've got two other messages that basically are also doing federated voting. And I guess I'll skip straight to questions. I'll just say in terms of status, we've got people implementing this. And, there's a couple things we still need to figure out in the protocol. And there's work that you're going to hear about now on formally verifying it.
Are there any questions remotely? Or no, there aren't.
Okay, sorry about going over.
That's one question.
Yeah, is it all right? Or
Yeah.
all right. Hi, I'm Shane Kerr. I think you mentioned that because you can only vote for things and not against them, that you avoid the stuck case.
For a nomination, yeah, not for balloting.
Okay, but it seems like the intuitive notion of stuck is missed there, because if not enough people vote for it, it will never proceed, right? Which, like, just to a layman, that sounds like it's stuck, even though formally it's not stuck, right?
Well, it's not stuck in that, like, you can always change your mind and vote for it, right? If need be, right? The problem with the not irrefutable messages, the ones you can vote against, is we can be in a situation where, like, I voted for it, you voted against it, you know, and now we're like, bummer, we'd like to actually make progress here, but there's nothing we can do because we're just not allowed to change our votes, right? Whereas if I nominate something and you didn't yet, and we're sort of not making progress, then you can say, oh, I have a solution, I'll just, you know, vote to nominate this as well.
So in that case, if I voted for something, can I revoke my vote?
You cannot.
Right. Okay. Okay.
But the thing is, like, there's not a problem with nominating multiple values, right? There's a problem with both confirming and aborting the same ballot, but not with nominating multiple values.
Okay. My second question, sorry, very quick, is a bit related. There's no clocks in any of this, right?
There's some timers. So the timers are not required for the safety or for the non-blocking liveness, but to kind of make progress in practice, it's kind of like there's timers and it's kind of self-synchronizing. So what happens is, as soon as you see a quorum that is at your ballot number, at your ballot counter, you arm a timer, which gets longer as the counter in the ballot gets bigger. And then when that timer fires, you move to the next ballot. However, if you see a blocking set that has a higher counter than you, then you bypass your timer. You just immediately bump your counter, because it means you've fallen behind and you'll never see a quorum at your counter value. And so that ends up that everyone's clocks end up roughly synchronized, as long as, like, the timer is much longer than the communication delay.
Okay, cool. Can we get a quick show of hands? Who has read a version of this draft? Okay, that's a few people. It would be great if we could get more eyes on it. So, I mean, David and his team have been working on this for some time, and just kind of significantly reworked this. This is a candidate for a piece of work that Dinrg could work on in the future. So if you have any opinions on that, please share that on the mailing list or get back to David and his team directly. Thanks, great work.
Thanks.
All right, moving on. Giuliano is going to talk about formal verification of Stellar.
Hello, can everybody hear me? Yep.
Get a bit closer if you can.
Yeah. Okay. So, can I? No. Oh yeah, it's a bird. Yeah. Okay. Okay. So I'm Giuliano. I'm a postdoctoral researcher at UCLA in Los Angeles, and so I'm going to talk about formal verification of SCP today. So the goals of this project are, first, to produce a formal specification of SCP, so essentially a formal version of the current internet draft. Then to produce a formal proof of the intended properties of the protocol that is specified. And finally, to produce a formally verified reference implementation. So let's start with the specification. So what is a formal specification? So it comes in the form of an abstract state machine, so with state and transitions. Here you have an example of a trivial specification of a door, which has two states, opened and closed. And the transitions are to open it, which you can only do if it's closed, and to close it, that you can only do if it's opened. So more complex specifications look like programs. So we can use a kind of programming language to write a specification. But there are some differences. The specification has a precise meaning, which not all programs have. And it is written for clarity. And finally, it specifies an envelope of behaviors in order to allow for implementation choices. Right. So why would we choose to specify something formally? Well, because it gives us an unambiguous description of what the protocol is supposed to do. Right, so this means that if you give me a trace of the calls to the API that is being specified, then it is very clear whether this trace satisfies the specification or not. And so the advantages are that it improves communication between the protocol designer and the implementers. There is no interpretation errors. It can be used as a test oracle, so you can test against it, which you cannot do with a prose specification. And you can verify formally that its intended properties hold. And also you can use it to formally verify implementations of the protocol. All right. So here are a few excerpts of the specification of SCP, which is underway. So here we describe the state of the system with 3 relations that you can think of as SQL tables that each contain what the nodes did in the protocol. So for example, vote contains information about whether node V voted for either commit or abort for ballot B. Right, so this is the state of the specification, and now we can specify what are the transitions, which are called actions in this language Ivy that we're using. So here you have the action vote commit, which models a node voting to commit a ballot, and so it can happen only if the ballot number is strictly greater than 0, and also if for all ballots C, if C is strictly smaller than B and C has a value which is different from B, then this node must have confirmed ballot C as aborted. If those 2 conditions are met, the action can fire, and it will update the state of the system by inserting a row in the vote relation consisting of V, which is the node, B, the ballot, and commit, what the node is voting for. Right? So similarly, this is the confirm action, another example. So of node V for ballot B, statement S, and according to information from node set Q, which requires that Q is a quorum, and that all members of this quorum accepted statement S for ballot B. In this case, we update the confirm relation. All right. Okay, so but is the specification actually what we want? Is it correct? So what we can do to check that is produce a formal proof, which will prove that all possible executions of those actions of the specification will satisfy their intended properties. So what are the intended properties for SCP? So David talked about that earlier, but I will repeat. So we need 2 definitions to state those properties. First, intertwined nodes, which are nodes whose quorum intersect at the well-behaved node. And intact nodes, which are nodes which are intertwined and additionally are part of a quorum of well-behaved nodes. So given those 2 definitions, the first property we want SCP to satisfy is that it's safe, meaning that no 2 intertwined nodes will ever externalize different values for the same slot, and that SCP is non-blocking, meaning that intact nodes always remain able to externalize a value. They're never stuck. All right, so why do we want to prove formally? Can we just maybe do an informal argument like is done in the SCP white paper? Well, this is because distributed protocols are notoriously hard to get right, and informal arguments usually do not cut it. So to convince you of that, I have one example. This is the Cord protocol, very famous protocols cited about 13,000 times according to Google Scholar. And so published in 2001, and the author says that attractive features of Cord included simplicity and provable correctness. So this is a protocol that implements a distributed hash table in a peer-to-peer network. So unfortunately, about a decade earlier, another researcher looked more closely at Cord using formal methods, and she found that in fact not a single one of the properties that Cord was supposed to satisfy was actually true. So this means that if you implemented Cord according to the description in the initial paper, then you got a system that risked becoming inconsistent. All right, so our formal proofs are a realistic goal. So yes, the formal proof technology has been maturing very fast, and very complex systems have been recently proved correct, such as full C compiler, hypervisors, cryptographic libraries, and so on. So we want to do that for SCP. So what is a formal proof? So it's like a mathematician's proof, but it's much more detailed. And because it has so many details that we need to keep track of, we want it to be machine checked. So a program will verify that the proof is correct. So let's take a very simple example. Let's say we want to prove a logical statement. We want to prove that I assume that A implies B, and I also assume that B implies C, then I can conclude that A implies C. So how do I prove this formally? Well, by producing a proof tree, which is a tree like this, where the leaves are the assumptions here and here and here, which can be canceled like this one. And the root is the conclusion, which we want here. And every node is obtained from its children by applying a basic rule of logic. So here and here we apply the rule modus ponens, which is a basic rule of logic. And here we apply assumption elimination, where we take an assumption, we eliminate it, and we put it in the goal. So that's a very simple formal proof. But as you can see, if you want to prove anything interesting in this way, it's going to blow up completely and be very, very tedious. So in fact, people have tried it, and here I have the example of a proof of the Raft protocol, which implements a state machine replication. This proof is done with the Verdi framework, and it took 50,000 lines of proof to prove that just 500 lines of code are correct. So obviously, we don't want to do something like that. And what's great is that we now have amazing automated solvers like Z3, for example, which can find those proofs automatically for us. So they're really amazing tools, but they're also not all powerful. So what we want to do is strike a good balance between automation and manual proof. So we're going to do this for protocols like SCP using the concept of an inductive invariant. So what is an inductive invariant? So let's say I want to prove that property P holds for every reachable state of the specification. Well, to do that, I'm going to find a property, an inductive invariant called inv, such that three things hold. First, the invariant holds in the initial state. Second, if I assume that the invariant hold in any state, and I take one step of the specification, one transition, then the invariant should hold again. So it's preserved by the specification. And finally, safety, it implies the property P I wanted to prove. So in fact, this is just proof by induction, like maybe you learned in high school. And it's illustrated by the dominoes here. So if you tell me that the first domino will fall, and you tell me that if a domino falls, then the next will also fall, I can conclude that all the dominoes will fall. This is the reasoning. Okay, so we can use this in a proof method called deductive verification, where we ask the user, the human, to come up with this inductive invariant. This is a creative process. And then we use an automated prover to check the three properties of that we saw before automatically. All right. So in the end, it will look like this. So we start with the protocol specification, the invariant that the user came up with, and the safety property. So this is the job of the user. And then we feed this to our tool called Ivy. The front end of the tool will translate all those things to logical formulas in first-order logic. So those are the three properties I talked about earlier that will be translated in first-order logic. And then we will send those formulas to a first-order SAT solver, which is automated. So this is the job of the machine here. And the solver now will answer the question of whether there is a counterexample to the properties. So if it says no, there is no counterexample, it will also produce a proof, and we're happy. We have proved that our protocol is correct. It might also say yes, there is a counterexample. So this is then a bug, and this can mean two things: either the invariant that the user gave is incorrect, or there is an actual bug in the system. So the user has to go back here and modify the invariant, the system, or both. And finally, sometimes the solver, because it's not all powerful, it can also say, I don't know. And in this case, it's a little bit annoying because we don't know what to do. But so in my research, I proposed some new techniques to make sure this doesn't happen by using what we call decidable fragments of first-order logic. Okay, so here is, as an example, SCP's inductive invariant. So this is the property that we want to prove, P. So we want to show that if two nodes confirm two different ballots as committed, then the value for those ballots is the same. Unfortunately, this property alone is not inductive because it doesn't say anything about the rest of the state of the system, such as vote and accept messages. So to make it inductive, we have to add a few properties such that like a node will never accept both commit and abort for the same ballot. Also, a node, if it confirms something, then as heard from a quorum accepting it. And finally, the main invariant, the main property, which is that if a node accepts something as committed, then it means that all lower incompatible ballots have been confirmed as aborted, or this particular node accepted something as committed with the same value and at a lower ballot. Okay, so current status of the project. So there, we have a specification for SCP with formally verified safety property, and next I'm going to work on producing a formal document out of this specification that would be readable along with the internet draft, then prove the non-blocking property and produce a verified reference implementation. So if you want more information on Ivy, so the prover that we're using, or the verification techniques, you have a few links here. So this concludes my presentation. And so if you're interested in formal verification or would like to apply it to other projects, please come talk to me. I'll be happy to talk to you about that. Thank you.
Great. Thank you very much.
Carsten Bormann. So as usual, in formal verification, you now have a proof that what you modeled holds. How do I know that what you modeled is actually the protocol? And what techniques are you using to get congruence there?
Yeah, so that's a very good question. So in this instance, we're still in the process of defining the protocol, so that makes it a little bit easier because, I mean, we're defining it, so there's no existing protocol that we want to match. But if we could also check that an existing implementation corresponds to the specification by using the specification as a test oracle. So what I could do is run the system, collect some traces, and then using a model checker, I can automatically check whether those traces satisfy the specification, and then I can judge whether if there's a problem, I can judge whether it's a problem in the specification or a problem in the implementation and fix either of them.
Yeah, the specification in the end is a set of English language sentences, and that's what the implementer implements. So having something like the tool you just alluded to, that would be really useful.
I believe so. Thank you.
Wes Hardiker, ISI. I'm pretty much going to say the same thing. We had the same question, but can you back up to the slide with the long list of proofs?
Invariance?
Yeah, that one.
Yeah.
So to put what I think he said another way, we're not positive that that's complete because that came with human analysis of actually what you said was the words, right? So we hope that you've found everything that you need to include in that in order to generate the proof, correct?
So this proof here is actually checked by a machine. So it's not possible that I missed something. The machine would catch it. But this is a proof about the formal specification, right? Not about the prose specification. Was that the question, or?
Yeah. So hacking involves using things in ways that you didn't expect it to be used, right? And right. So if there's alternative inputs, or I mean, you gave examples of, well, you have to make sure that somebody didn't vote both for and against something, and then you have to think about, well, what if they voted twice? What if, I mean, all these types of things, and making sure that there's no other forms of input that could go into the system that hadn't been accounted for in the
right. So yeah, the specification says you're not allowed to do those things. So now you have to check that in reality you don't do them, and you can also formally prove correct your implementation in that case. Yeah.
Good. Quickly, we hate to do this in a research group meeting, but we have to cut the line after Turles.
Okay, my name is Keshav, University of Waterloo. Do you have any timers or timeouts in your model?
So in this model, there's no timers because for now I only prove safety, and timers are used for progress.
But you could have safety violations from race conditions, possibly.
Yeah. So this proves that all possible race conditions are covered and will not cause a safety violation.
Okay,
yeah. So it looks to me as if I'm converting all these invariants to assertions that are, automatically, for example, put in the code, and that's fine. Then the system will never do something that violates these. But I think it doesn't tell me why the system shouldn't kind of stop at a point in time and says that the assertion has failed, right, in the code.
Yes, so this is static analysis that you do beforehand. So there is no assertion put in the code. We analyze the code beforehand, and we prove that all executions will satisfy the assertions.
Right, but I mean, the assertions didn't come from analyzing your actual code, but from the human input, right? So that's, I think, the issue, right? Unless you can derive these rules automatically from the code, that's, I think, when we're getting into, I think, what Carsten was saying.
Yes, so here we analyze the formal specification, which was written by hand by me. Yeah.
Okay. Thanks a lot, Giuliano. Okay, let's move on. So Jean-Luc is going to talk about distributed delegating mappings.
Thanks. Okay, so my name is Jean-Luc. I'm joined today by Sydney and Colin, who are in the back. Can answer questions afterwards if necessary. We managed to sneak a draft in under the deadline for these things called distributed delegated mappings. Basically, what this presentation is about is we've heard a lot about the SCP protocol, and now it's time to build something on top of it. So if you've been to previous meetings, you've probably seen some of this, but a little bit of motivation before we start. There are a lot of mappings on the internet. So if I want to send an encrypted email to, say, colin@email.com, we have to rely on a centralized source of trust, in this case, the email provider, to give us Colin's public key to encrypt the email. So that's one problem. We have this mapping from email to public key that requires a lot of trust in the email provider. Even worse, that email provider can unilaterally revoke that mapping, so we would never be able to send Colin an email, or it could change that mapping unilaterally, so we would be, encrypting with the wrong key. So there's this issue of unilateral revocation. And the last thing is that there's a lot of these examples that we'll get into on the next slide, and they all have different interfaces. So the goal of this is to provide a common interface for authentication in mappings and to provide support for delegation. So there, as I said, there are lots of use cases. For domain mappings, you're mapping zone files where you have to trust the domain roots. In PKI, you have to trust the CAs. You have HSTS preload lists that you have to manually insert into browsers. And for example, if you want to allocate IP addresses, you have to trust autonomous systems when you're doing BGP and stuff like that. So there are a ton of point solutions. What we want to do is we want to combine those. And so the basic structure is we have all these applications, and we have this nice consensus protocol that can provide a public append-only log, and we need some glue between the application and the consensus protocol to actually make use of that. That's where these delegated distributed mappings come in. The really important thing is that a lot of these mappings have a delegation structure, and so we want to make sure that we have explicit support for that. Okay, so delegate mappings. Basically, the overview of this is for every application, we're going to have a set of tables. And the tables are basically lookup key value mappings. And the values can be either the items that you want to secure and make available. So those are, say, zone files or keys. Or you can delegate a subspace or a sub part of the namespace to another owner who will kind of modify and maintain that portion of the namespace independently. So that's where the arrows are. What we're going to do is we're going to drill down to the individual components and then build it back up. So the first part is a cell. That's the basic record of delegation. It has a couple of fields. It has a creation timestamp, a revision timestamp, and most importantly, a commitment timestamp. That's what's going to provide a measure of security against unilateral modification by the authority that is granting the mapping. So, for example, the email provider for Colin can say, you can specify a public key, and it's guaranteed to be valid until at least this time. Throughout this presentation, all of the red kind of squares are going to be fields that the authority is going to be modifying, and all the green squares that we'll see in a bit are going to be values that only the owner of the cell, so Colin in our email example, can modify. The white ones, anyone can modify depending on the operation. So the contents of each cell can vary. If it's a leaf node, it's just going to be a value cell. It's going to contain the key for the owner who can modify and update the value stored inside, a signature to authenticate it, and an application-specific value. So that could be an email key, it could be a domain zone file, it could be a binary hash, it could be anything you want. The goal is to be as extensible as possible. And if you want to delegate something, you're going to use a delegate cell. And that has the key that the public key of the entity that you're delegating to, and it has a signature from the authority and a subrange of the namespace. You can see why it's important that we kind of specify which fields are modifiable by who, because in this case, the permissions are a little bit different. Only the authority granting a delegation can modify the actual namespace that's being delegated. It wouldn't really make sense for the delegee to be able to just update their own namespace. Okay, so now that we have these cells, we can form these tables that we were talking about earlier, which are lookup keys to cell kind of mappings. Basically, there is one key that is the authority over the table who can insert new mappings. And there's a rule for how we generate delegations. So unfortunately, we can't just let the authorities do whatever they want. We have to ensure that they're delegating namespace ranges that are within their own zone of control. So there's two delegation rules right now. There's a prefix delegation rule and a suffix delegation rule. You'd use prefix delegation for IP address allocation and suffix delegation for example, domain name delegation. Yeah. So yellow is delegation, and you can also have value cells in there that just allocate individual mappings. Okay, so it's not tables all the way up, unfortunately. You have to have a root somewhere. And so what we propose is a root key listing. It's going to store the root key for each namespace that you have. Now, big question is how you actually manage this table, and we can talk about that in a little bit. But for now, we can look at it in terms of a list of root keys for each namespace, an application identifier to identify what exactly you're using that series of tables for, and a signature. So yeah, it's a list that kind of links down into the tables. Once we have all these parts, we have cells, we have tables, and we have the root key listing, you can actually do something with the structure. So this is what it will look like. You start at a namespace key, and that key controls a table, which can delegate ranges of its namespace to other tables, which can, arbitrarily go on forever almost, and eventually delegate or assign a mapping to an individual entity. And the really nice part about this is that the same structure can be used for a ton of different applications. It's really generic. So if you want to do domain delegation, you start off with the root DNS key, and you have a series of suffix tables where I can allocate .com to be managed by a certain registrar. That registrar can say a.com is managed by a specific company, A & Co. And A & Co can assign a specific zone file and a manager for that zone file to a specific subdomain, so x.a.com. Exactly the same thing can be used for IP prefix delegation. So you have a different key, a different application identifier in the root key listing, and you do prefix delegation. So the root DNS table, or not DNS, the root IP table can allocate /8 block to Aaron. Aaron can allocate a 16 block to Stanford, and Stanford can allocate a specific IP address to, for example, Sydney's public key. So some kind of common operations just to walk you through how this would work is that if you want to create a delegation, all you do is have the table authority insert a new delegation cell into the table, and to create a new table for that delegee to then create its own mappings. And the proof of those additions to the overall structure is simply passed to the consensus layer that we'll talk about in a couple of slides. Next, if you want to do key rotation, this is really, really easy because all you do is you update your own key in the cell, and you just sign it again and submit it to the consensus layer. So that's why separating these fields by their modification rules is really important, because it allows the owner of the cell to, without needing authorization from the authority, to update and rotate its own keys. But it can't modify the commitment because that's the delegator's priority or prerogative. Finally, you can look up arbitrary mappings in the table by starting at the root key listing, finding the root table, and then following by either prefix or suffix match the entries in the delegations until you reach the value cell that you want to find, or null. All right, so this is all well and good, but you have to secure the table structure somehow, which is why you need a consensus algorithm. So that's what's going to be providing the safety and the consistency between different nodes in the network to actually provide these mappings. And really, the interface is really simple. You can pretty much use any consensus protocol that you want, as long as it actually does consensus, and it provides a way for the application to specify which proposed modifications are valid or not valid. So for example, we can use SCP really easily by batching update proofs at the same time, and then using the validity function callback to actually specify which delegations are correct or incorrect. Okay, so some considerations. We talked earlier about this root namespace, and that's kind of up in the air as to how we want to manage that. What's pretty easy right now is to just use one root key to manage the root key listing. What's important to recognize is that this is actually a little bit more secure than a centralized point of trust, because you can actually provide these commitment timestamps to lessen the amount of trust that you have to put in the root authority. You can use threshold encryption or make a vote against root authority, so that's still kind of open, and we would love discussion on that. Second is spam. The reason we have this root key listing with a limit on which entries can be in there is to prevent you from just blowing up the entire structure. The same problem applies to individual delegations. So as soon as you delegate a range of the namespace, you kind of let that go, and the delegee can do whatever they want with their table, which is an issue. So a couple things that we're working on is looking at delegation quotas for the size of the tables that you can actually delegate, or making delegators responsible for their delegees. So kicking them out of the tables if if they become a problem. And finally, in terms of scale, this really depends on how we run the consensus algorithm and the data structures involved. How many full consensus nodes do we need? And is the system scalable to a per user record level? That's a question that we're looking into. Okay, so we're going to keep making changes and updates to the draft, but in the meantime, we would love any questions that you might have.
Hello, Brian Trammell. Cool work, cool draft. I really like this presentation. I have a little bit, actually, I think I kind of want to pick on your considerations at the end. It's,
Sure.
So like, this is a pretty elegant solution to sort of the technical problems, but the technical problems are the uninteresting problems, right? How, like, yeah, so I mean, like I don't exactly see how we take sort of some of the more, the more delicate questions of governance, who gets to say what, and map them onto the consensus protocol. Do you have any thoughts there, or would this be the correct place for that? Or
what do you mean by governance?
Okay, so like the consensus protocol basically has a K of N, right? You send things off to various observers. The observers are, presumably incentivized to not lie. How does the sort of the larger questions of who binds their sort of their publishes to where, how do these questions, I mean, so like go 2 slides back.
Yeah.
Wait, no, one more slide back. Yeah.
Yeah.
This question.
Yeah.
Question mark. I'll turn this back around. And so this is not a please answer this question. This is not a gotcha. This is a think hard about this.
Yeah.
And I'm wondering, I don't know if there's a question for you or for the chairs, if this is the right document for that to be in, or would there be a different document for that?
I think it would have to be in this document.
Okay. Yeah. So I would encourage
Okay.
thought about that, and I'm willing to help. So.
Okay. Yeah, that'd be awesome. Thanks.
Hello, Hirotaka Nakajima. So could you show me the IP prefix derogation slides? Yes, I'm not sure about I couldn't read the spec, but so for example, like IP prefix derogation. So if like in this case, like Stanford's transferred address to the company which is out of the A-link, that's needs, in this case, like we need to move the entry to the another, like for example, APNIC or other things. So this scheme can do this kind of things. So like indirect redirect to the delegates to the other.
Okay. So if you want to move blocks between delegations,
exactly.
So that's why we don't say, hey, you've committed to delegate this forever. So that's why there's a timeout on that. So obviously, if you're Aaron and you're going to lose a block, then you should probably know about that. But yeah, there's a mechanism. So once the timestamp expires, the table authority can just modify the mapping.
Okay, thanks so much.
Okay, thanks. Interesting work. So we are now moving with Shea Bano from London. And right.
All right. Are you ready?
Hello? Hi, can you hear me?
Yeah, you bring. Right. Keep talking. I bring up the slides.
Okay. Okay, hello everyone. I'm Bano. I go by my second name. I'm a postdoc in University College London and also on the research team of ChainSpace. And how do I move on to next slides?
By telling us.
Okay. So I'm excited to present today Coconut, which is a selective disclosure credential scheme that I developed with my co-authors, Alberto, Mustafa, and George, who have the same affiliation, that is UCL and ChainSpace. Next. So first, what is a selective disclosure credential scheme? So in very simple words, it is a cryptographic scheme that allows to issue and verify credentials in such a way that the credential can embed multiple attributes, for example, age, name, and so on. And the selective disclosure means that you can choose, a user can choose which attributes to reveal and which attributes not to reveal when they show the credential to the verifier. Next. So Coconut, as I mentioned, is a selective disclosure credential scheme which supports the following properties. It supports blindness, unlinkability, threshold authorities, and non-interactivity between those authorities. Next. And here is a very high-level overview of how Coconut works. So as you can see to the right side, there is a set of n authorities, and a user sends a request to each of those authorities, and each of those authorities then issue a partial credential. The user gathers those partial credentials and consolidates them into a single credential, and then it can re-randomize that credential and use it across multiple verifiers. Next. Right. So let's look at each of the 4 properties that I previously mentioned. So what do we mean by threshold authorities? So that basically means that we don't require all the n authorities to be online. In fact, only a subset of them have to be online or honest to be able to issue the partial credentials and for the users to gather them and consolidate them into a single credential. Next. So here's a diagrammatic representation of what I just said. So we have n authorities, but we need only shares from t of those authorities. Next. Then by the second property of non-interactivity, we mean that the authorities do not have to coordinate, synchronize, or interact with each other. In fact, they can entirely independently issue those partial credentials. Next. By blindness, we mean that the authorities issue the credential without learning any additional information about the private attributes which are embedded in the credential. And by unlinkability, we mean that it is not possible to link multiple showings of the same credential across multiple verifiers, even if all of the Coconut authorities collude with each other. So there have been other systems in previous literature which offer a subset of those properties, but Coconut is the first scheme that offers all of these properties. Next. So Coconut is based on 3 existing schemes, which I have cited below. And you can read full details about the cryptographic construction of Coconut credentials in the paper, which I will link in one of the following slides. So we believe that it's very useful to integrate Coconut into blockchains. The idea is to enable only authorized users to enable certain smart contracts. So you can imagine that in the standard web, we might want to offer certain services only to authorized users, usually by using username and passwords for authentication. But it turns out that it's not that straightforward in the context of blockchain, because carrying on with the previous example of usernames and passwords, that would basically mean that all the blockchain nodes process the password, which is obviously not nice from a privacy point of view. The other alternative is to get users to get a randomized credential from a single trusted third party. But then that does not align with the decentralization goal of having a distributed ledger in the first place. Next. So we feel that Coconut addresses those issues, and it can be integrated into blockchains in one of these two scenarios. So in the first case, the authorities could be located outside the blockchain. And this is the default model that we assume through the rest of these slides. But the other alternative is also to more deeply integrate it into the blockchain, for example, by allowing the blockchains to serve as Coconut authorities and issue partial credentials. Now, as you might imagine, that this makes sense only in the context of, I'm still on the previous slide.
Sorry.
That seems feasible only in the context of permissioned blockchains, because there the identities of nodes are relatively more persistent, but might need more consideration in the context of unpermissioned blockchains where the churn among nodes is pretty high. Next. So we implemented a smart contract library for ChainSpace and also the same library for Ethereum. And the smart contract has different functions. So a set of nodes can use the create function in the smart contract to create a set of Coconut authorities. The users can use the request function to send a request to those authorities. The authorities can issue the partial credentials to the users using the issue function. And then any third party can use the verify function to verify that the credential has actually been issued by the Coconut authorities. Now, here is an application of privacy-preserving petition that we built on top of the ChainSpace, the Coconut smart contract library for ChainSpace. So the idea is that several authorities manage a city, for example, Barcelona, and they want to issue some long-term credentials to its citizens. This allows the citizen to obtain a credential from the Coconut authorities and then use the same credential across multiple different petitions without revealing their identity or being linked across those petitions. Next. So here's the diagrammatic representation of this privacy-preserving e-petition smart contract. So the part on the top happens only once, where the citizen provides a proof of identity to the Coconut authorities and obtains a long-term credential corresponding to that proof of identity. And then the citizen can use that credential to sign multiple petitions across different campaigns without being identified or traced. Now, the use of Coconut in this scheme enables three main properties. So the first one is that the blindness property prevents the authorities from learning the citizen's secret key and misusing that information to sign petitions pretending to be that user. Next. The citizens can reuse the same credential multiple times across different petitions while remaining anonymous and unlinkable. Third. And the use of multiple Coconut authorities allows prevention of the risk if there were a single authority and that authority goes rogue and creates arbitrary credentials to create fake votes on behalf of non-existent users or citizens. So this application is currently being tested in our Barcelona pilot, which is part of the Decode project, consortium of 14 partners from across Europe, which funds ChainSpace and Coconut. So we also implemented two other applications on top of the Coconut smart contract library. The first one is a coin tumbler, and the second one is a censorship-resistant distribution of proxies. So I will very briefly mention these other two applications because we don't have that much time. But with the coin tumbler, the idea is that a user can buy goods or services from a merchant without being identified. And the design is very simple. The user deposits a certain fund and shows the proof to Coconut authorities, which issue a token to the user. And then the user sends that token to the merchant, and the merchant can provide that token to withdraw that amount from the buffer. So the properties that Coconut enables is that it prevents a single authority from creating coins to steal all the money. And Coconut prevents a single authority from blocking the issuance of tokens. And the other application is that of censorship-resistant distribution of proxies. So a common way to circumvent censorship in censored countries is the use of proxies, but then proxies themselves become the target of censorship. And there are a number of volunteer, not a number, but a few volunteer organizations such as Tor that run these proxies. But it would be useful for those volunteers not to be able to be linked to those proxies, for example, to enable coercion resistance. So this application allows volunteers to run verified proxies, as in proxies verified by coconut authorities within censored countries, without those proxies being linked back to the volunteers. And users know that it is a trustworthy proxy because it has been verified by the use of coconut credentials. But at the same time, proxies cannot be linked back to volunteers. Next. So moving on to performance. The performance is good, signing is fast, and signing takes about 3 milliseconds, and verification takes about 10 milliseconds. Next. The size of credential is constant in two group elements, no matter how many attributes have been embedded in the credential, and no matter how many coconut authorities are there. Next, we evaluate how coconut scales in the number of authorities. So issuing of the credential is linear in the number of authorities, and verification is constant time. Next. And finally, we evaluate what is the client perceived latency, in that how long does it take for a user to get partial credentials back from T of the N authorities. So we set up 10 nodes on Amazon Web Services across the world in 10 different countries. And on the x-axis, you can see the threshold parameter. So for example, 1 means that only 1 partial credential is needed. 2 means that 2 partial credentials are needed, and so on. And on the y-axis, you can see the latency in milliseconds. So as you can see that the latency increases about linearly in the size of T, which is the number of the threshold number of authorities that are required to respond. Next. So there is a slight jump after T is equal to 2, which is because the 2 of the nodes are located in Europe, so they respond quickly. And the jump is because the third node is located outside Europe. So as expected, the farther the nodes, the longer it takes to receive all the responses and then consolidate them into a single credential. So the paper is available online, and you can read more details about the cryptographic scheme, the smart contract library, its evaluation, the 3 applications that I discussed, and their evaluation and benchmarking. So to conclude, I presented Coconut, which is a selective disclosure credential, and it supports threshold issuance, which is suitable for distributed ledgers. And it supports re-randomization of those credentials to allow the same credential to be used across multiple verifiers, which enables privacy. So on that note, I conclude. Thank you. And if there are any questions, I'm happy to answer.
Thanks a lot, Banu. Are there any questions in the room? There's one coming up.
Hi.
Hi, Banu. Robin Wilson. Thank you very much for that presentation. I have one sort of question and one observation. The question relates to what you said about Coconut being the first scheme that offers all the properties you described, so blindness, unlinkability, and so on. I'm aware of 2 other selective disclosure architectures, UProve from Microsoft and Identity Mixer or IDMix from IBM. And I wondered if you had investigated those in the course of your initial research.
Sorry, one was ID Mix from
and then
IBM,
the observation
and what was the first one that you mentioned?
The other one, UProve, just the letter U and then prove from Microsoft. So both of those are cryptographically supported protocols for selective disclosure or for blinding some of the attributes that are embedded in a single credential. So the observation was about when you were talking about chain space and its use in smart contracts like the Barcelona e-petitions. you made two assertions. One was the user can use a single Coconut credential to sign multiple petitions while remaining anonymous and unlinkable. And the second one was the use of a decentralized architecture mitigates the risk of a single authority going rogue and issuing multiple bogus credentials. And my question was, if the user can use a single Coconut credential to sign multiple petitions while remaining anonymous and unlinkable, isn't that risk present anyway? Because a user can just generate multiple bogus identities and sign as many petitions as they want. So you've mitigated the risk of a rogue authority, but you haven't mitigated the risk of the use of multiple unlinkable credentials to say.
So I believe that the way the smart contract has been implemented, the verifier can check that the credential has been the credential that has been verified has been used only once to cast a vote. So it keeps that record.
Right, but if the person doing the voting is anonymous and unlinkable, they can have multiple credentials and vote many times. Thank you.
Thanks.
Okay, but I'll read this back again. Thank you.
Hi, this is Daniel Cohen-Gilmore. Just to clarify, I think that the point that Robin was making was that if the authorities are in fact distributed and not colluding with one another and registering the same population, it seems plausible that an individual could register themselves with multiple authorities, thereby creating multiple identities with which to vote. I think that was the question.
So in this case, for example, the proof of identity would be something which the government has given to the citizens of Barcelona, based on which they can get only one credential from the authorities.
So is there a coordination then between the authorities to ensure that one person doesn't manage to get a credential from each
There's
of the
no
distributed
coordination
authorities?
between the authorities, but for like a single proof of identity, they issue a credential, like a partial credential only once.
David, my suggestion, Stanford. I guess I'm confused about the confusion. I'm imagining one credential says you have the right to vote, another credential says you have the right to drive. Say, right? I mean, wouldn't the different authorities be vouching for different things, such that you're only using your voting credential to vote? That like you live in Barcelona to vote for something in Barcelona, or
Sorry, say that again. Is your question related to the proof of identity, which is used to, as proof of being a citizen of Barcelona? Is that what you mean?
Yeah, I mean, presumably there's only one authority that's actually telling people that certifying people as residents of Barcelona, right? So I think the confusion is if there's more than one person who can say that you're a resident of Barcelona, then you can get two credentials that you live in Barcelona. But if there's one authority telling you that you're a resident of Barcelona, another authority telling you you have the right to drive, another telling you, something else, then I don't see why double voting
scenario,
would be
just
an
to
issue.
clarify, we imagine that the Coconut authorities would still be under the control of the government of Barcelona, but they would be run by, for example, different departments. So it's not that anybody can become a Coconut authority. In this case, for example, due to the sensitivity of being able to authorize citizens, they would have to come from the government, but not from within the same department to ensure some sort of transparency or distribution.
Okay.
Thank you very much.
Okay. Thanks again, Bano. We have to move on, unfortunately. Okay, bye-bye. All right. Who hasn't signed the blue sheet yet? Okay, that's a fair number. So we have to make sure that we get a big enough room next time. So let's add you on the list.
Okay, good morning. I wanted to talk a little bit about, how... Closer? Okay. Yeah. Right. So I wanted to talk a little bit about how I can see that, Dinrg and Anima working group in the IETF, could have really a lot of common interests, and explain a little bit about what we've done and how it could relate to Dinrg. So in summary, I think there are two directions, right? One is you can, in Dinrg, leverage Anima work that was done to make life for what you build easier. And in the opposite direction, would really love to see, output from Dinrg to be something that we could leverage as future steps in Anima. So, and we actually have a history of coming from the output of an IETF working group, and that's NMRG, which started to define a framework architecture for autonomic networks in RFC 7575 and 7576. And the goal there was to define in the framework an evolution of networks to be built with self-X, as it was called, right? Where X stands for anything that you can think of, configuring, healing, managing, optimizing, protecting. And so the key building blocks would be these autonomic service agents shown here in the middle that would have self-knowledge, network knowledge, feedback loops, and basically, in a distributed, decentralized fashion, provide these self-X functions. And they would be embedded in, on the underlying stuff somewhere on the bottom, right? You have the network operating system of the network equipment, and then the magic autonomic network infrastructure, which would basically take away all the pain stuff, that the autonomic service agents wouldn't want to reinvent by themselves, but that, they'd need to come up. And then on top of the ASAs, some intent-based network management that would allow you to operate the network not based on millions of lines of CLI or Yang, but instead of only what really the network operator is interested to tell the network and really wants to have enforced. And that is still a big ongoing discussion. So with that output, the charter of Anima working group was built in the IETF. And so the first charter round was really around building the ANI, the autonomic network infrastructure, and also to have two proof points for the ANI. And so the one proof point, and those are informational. The first proof point is how can we use the ANI not in the, 10 years, wait to get these ASAs done, but in current existing networks, let's say, for example, in the context with an SDN, to automate the management plane, use the ANI as the management plane to really ease the life of SDN controllers. And the second one was really the autonomic assignment of address prefixes in the network through ASAs. And there are also prototypes being built for that. So that work of this charter is finishing up. Most of the stuff that we've done there is, in various stages of IETF, IESG review, RFC editor, or as this 8368 already out as RFCs. So here is the, more fine pointed overview of the autonomic networking architecture according to Anima. So we see up here intent and reporting. Then these autonomic functions really are just, the word for, a set of distributed ASA that does something useful. And that's pretty much as much as we've gotten to. So we haven't really worked on this other than in the reference model describing the structure of these elements for the purpose of saying what does the ANI need to provide to these ASAs that we think would be great not to have to reinvent in every ASA itself, right? So what the ANI provides in the first place is that any type of, fresh from the vendor unconfigured device would be given a domain certificate so that you can have secure communications between these nodes. The second, and that's basically done by this bootstrap protocol, Brewski Secure Bootstrap, that is basically providing the certificates. The second one is autonomic IPv6 connectivity through the ACP, of course, leveraging the domain certificates and therefore establishing really IPv6 reachability, IPv6 communication between ASAs that you want to build so you don't have to care about that. And the third one is the grasp signaling, which basically provides the messaging layer, whose most important element is the ability to do also discovery of each other, because if you want to self-orchestrate yourself, discovery of other nodes, of other, ASAs, autonomic functions, whatever you want to discover is, of course, a core functionality, right? And then, of course, the whole thing could run just in an autonomic fashion where there is no NOC, or in the NOC, we equally have domain certificates assigned to all the existing wonderful current SDN nodes, or even in the future, right? There are a lot of things that are really done a lot easier in a centralized fashion. So what we've been trying to evolve from is, not autonomic, but, we want to be the self-orchestrating, self-configuring system, however many parts are distributed, decentralized, or centralized. So that was just the text for this slide. So where we are today, current, investigation, futures. So we wanted to start doing our rechartering and see, which additional blobs we want to take on and how much to chew in there. So right now, today, there is NMRG, a lot of the folks over for a whole day of discussing intent. So little progress was made about intent. It's now the big buzzword in the industry. Everybody's talking intent. I think 2 people talking about intent will have at least 3 different options what it means. Then the distributed services, right? On that side, there are really 2 big interesting things, right? Is what distributed services would we really think to be the next ones on the line for IETF adoption? Because IETF really means we want to have things that are so important that, a majority of networks would like to have them. And, seeing these things like distributed consensus and others, I think they're really good things that could start coming in that direction. Of course, the industry is fairly slow in adopting new technologies. So I would love to see, proposals of what we feel could move into the IETF there. Yeah, I think that's really the core question. And then, for us coming more from the bottom side, the question is how to build these distributed services, right? So what are the common methods we use? We've primarily been thinking about how to help developers. Things like the formal verification, of course, could be cool things if we could establish at any point in time standards there. But of course, the ANI itself, we have worked it out, I think, well, but I think there are always things for improvement, and that's what I wanted to focus on to give an idea of, what problems would be solved if applying the technologies that, the INRG seems to be looking right now would be applied to the ANI. So, but ANI itself is not doing anything to user traffic or user control, right? It's just a management plane, right? So anything that you want to build to basically distributed routing protocol improvements, distributed addressing, all these things, we're just the management plane, right? So you can invent anything there for actual user traffic, user control without conflicting with the ANI, but actually leveraging it, right? And so to understand what the main purpose of the ANI is in the context of actually building distributed things, right? Try to figure out how difficult it is to get from unconfigured boxes to the ones where these distributed agents, the distributed software can actually work nicely well without having to pull itself out of the mud and not knowing how to do that, right? And so the typical example for which we built the solution is, right, how do you build, for example, autonomic distributed auto configuration of addressing and routing? If your agents themselves depend on the addressing and the routing to work before they can do their distributed job, right? And the solution here, of course, is you build an arbitrarily complex system to do, distributed address assignment, distributed routing, and all these things. You let these nodes communicate each other through the ANI. So even when you're doing things completely wrong and your routing is broken, your agents can still reach each other perfectly fine through the ANI. Right, which is also why we're very simple, and what the ANI is doing there would definitely never be good enough for really more complex user traffic distributed routing and addressing. Okay, so let's talk about here to get to the point of how I just was starting to think about how to get to federated solution ACP domains, right? So that's the part which we feel fairly confident about really being nice. So this was animated, it's not anymore, so so ultimately what we want to have is basically a domain of all these wonderful devices here, right? We're representing them as ducklings. I'll explain this in the next slide why. That have their certificates and that perfectly well can talk with each other, right, communicate and do whatever fun distributed services these devices could do. But the question is, how do we basically get to that point of security that each of these devices has a certificate, right? So our terminology is we start out with a completely unconfigured device, we give it a certificate that basically expresses its membership in this network, in this domain, and that's what makes it a member. And that is actually the very interesting part, because this, from the point on that the devices have certificates, everything is really nice, and all these distributed, decentralized things can be done very nicely, but how do we get to this point? And so this is the process, this is the mechanisms that we have, and they're very much built on really looking at the, current PKIX architectures that we have in the IETF, take the best well-established protocols, extend them, and come to a solution that is fully automated and basically pulls these devices out of the mud and getting them enrolled. So the first thing is the model really is all around the domain registrar who's orchestrating the process and basically interleaving all the necessary steps. So the first thing is, a new pledge comes up, and basically you'll discover it, the registrar discovers it, figures out its identity, may go to a domain admission controller and say, how, the pledge with this identity would like to join the domain, get into the lake, and is that permitted? And there might be all type of policies with that. So the next thing is then, okay, so let's assume the pledge is permitted. Ultimately, I want to give it a certificate, but that means I want to configure the pledge. And that's, by the way, where exactly the notion of the duckling comes in. The ducklings are, historically in this security research, the objects that are very gullible, and let them, you can do anything you want to them as soon as you're the first instance, like, the mother duck that they see, right? And in many cases, that's by far not secure enough, which is why in Brewski we come up with the notion of a voucher where the vendor, the master here, is basically providing an attestation to the domain that this domain owns the duckling. So basically you provide that attestation, the voucher, to the pledge, and then the pledge says, okay, now you can configure me. And then the final step happens, you try to give the duckling a certificate. And now, because we're also wanting to establish distributed connectivity, we're also embedding the address of the new duckling into the certificate, so that we also have a secure mapping between the secure identity, the certificate, and the address it can use in the network. So this is all, if you look at it, all these components are, yeah, you can maybe, make them to some degree redundant, but they're all based on individual non-decentralized trust models. And so it would really be interesting to figure out how this overall security model could be moved into, a decentralized federated solution. And so this was basically a little bit how I was thinking about this, applying, blockchain distributed ledgers and the voting mechanisms to this problem space. Right, so the first problem that we have is we really have no good ways to express ownership of nodes, right? Who actually owns a node, so that he can basically express what should happen to it, right? And obviously those things could be done through distributed ownership and ledger systems. And if we look at, the problems that individual vendors might have to bring up systems like the MASA, through which this is done on their own, this might actually be a very interesting area to apply ledgers to and figure out how it could be done. On the other hand, you'll have, all these policies for these domains, right? And if you, for example, don't want to send up a domain that's owned by an individual entity, by the federated domain, maybe you want to have exactly a distributed ledger-based mechanism to establish policies for the domain, right? Which nodes are allowed into the domain and whatever other policies the domain should later enforce on itself. Which basically gets us to the main point, which is the federated domain member operations, right? Where we want to be able to say, okay, what nodes do we want to accept into the domain based on these policies? And then basically who is able to express for a particular device, whether it should come into the domain that would come from exactly that ownership ledger, and then the overall operations of the domain itself based on the policies that, you know, the management, the federated management has done, right? So that would be kind of maybe a starting point of thinking how to apply these federated, distributed ledger voting system and so on to basically get away from the prior slide shown state-of-the-art current technology, you know, single instance, you know, third-party trust methods. So yeah, that was pretty much it. Thank you very much.
Cool. Thanks, Solis. Is there any feedback? How does it resonate with you? Do you see a potential connection here? So one of the contributions of an IETF group is, of course, also to, you know, provide directions or, you know, options for next steps for IETF work. And so, yeah, Tudor's kindly, you know, came up with some ideas how this could look like.
This was a lot to take in, so I'm not sure. Can you go back a couple slides to the diagram you had with the, you know, yeah, this one. So I guess I'm wondering if there's been any talk or any interest in control over software updates on these devices.
We haven't even gotten to that point. Excellent. I mean, I hadn't even had the time to look into the suite. There's the working group in the IETF to do primarily all this software upgrade mechanisms, primarily in the IoT space, and of course, even more security mechanisms to be safe against the quantum attacks and so on. But we haven't really, in Anima, taken up and tried to integrate any output of that into this framework. Because, you know, the operating system that needs to be there below to allow that, we haven't, I'm not sure how easy it is to get that into the IETF.
Yeah, Gazmo, I think that's an excellent question. And what I see on this diagram are really not so many protocols. Some of them are protocols, but really most of them are actually documents that claim something and are signed by somebody else. You just click it away.
Yeah.
For instance, in the software update working group, the main outcome will be a document called a manifest that contains signed claims. And I think it's really interesting to see that we have all these various signed claims coming up. And some of them are legacy ones that really are originally have been designed to solve a different problem. Certificates were designed to pair names with private keys, with public keys, and yeah, we are using them in a weird way. Anyway, we are seeing all these documents coming up, and maybe one thing we should think about is, do we have something like a calculus for deriving assertions from all these signed claims that we get? So the people with the ties in this picture, they actually have to make decisions based on multiple of these documents. And of course, we can design all these documents to be different and come up with bespoke ways to make those decisions, or we can try to extract what exactly are the commonalities between all these signed claims and be able to actually construct new signed claims without having to necessarily define new software to understand and process them. And that's something that I would call security semantics. And I think it's a pretty important thing we need to understand in the next 5 or 10 years when we build systems that are becoming more complex than just this first simple example.
Right. Yeah, I mean, that's a great point. I fear that right now in the IETF, we're kind of a little bit in the opposite direction, where we're spending 90% of our time on, 5 or more variants of presentation layers and, different protocols that are doing the same thing. So, I mean, to an extent, if there's interest in the industry, it's hard for the, the IETF to push back. But yeah, that's the core, and that would be great to concentrate on. Yeah, so if there are no more questions, please, get back to me. My email address is there, and see what we might want to, think of, collaborate on. And obviously, we're always happy in the working group itself to take on presentations and contributions. What could be adopted in the future, of course, very open based on our rechartering.
Okay, great. Thanks, Jonas. All right, so next we have Bingyang talking about their current research work on decentralized Internet Resource Trust infrastructure. Does it? So, okay.
Good morning, everyone. I'm Bingyang from Huawei. Today, I'm going to talk about the decentralized Internet Resource Trust infrastructure. And I think this topic is relative to some topic presented today, including the mapping delegation and the consensus algorithm. So in this work, we collaborate with UC3M, CNIC, and China Telecom. The background is that some critical infrastructures, the trust infrastructures in the internet, are centralized, including the resource PKI, which is the trust infrastructure for IP addresses and AS numbers, DNSSEC for domain names, and the PKI for identities. So basically, these systems all have centralized or hierarchical structures, typically tree-like structures. In these structures, the root nodes often have privilege over the subtrees. Malicious or misconfigured roots can cause problems of the subtrees. So, but I'm not going to talk about the general problems and solution to this system. Instead, I will focus my talk on the resource PKI. The resource PKI follows the same hierarchy of the IP address allocation system, while the IANA is the root, and the IRRs, regional internet registries, and the national internet registries are the root of the subtrees. In this hierarchy, the parent node will assign a resource certificate to the children, and the children will have the address ownership certificate, which is a RC. Then the address owner can sign a root origin authentication, which is called ROA, to map the prefixes to the AS numbers. Then the fourth step is on the BGP routing plane. The BGP routers can rely on the ROAs to detect the root origin hijack attacks. That is to detect the prefix to AS mapping, the fake mappings. So basically, ideally, the RPK can help with mitigating the BGP hijack attacks. However, misbehaving RPK authorities cause risks to BGP. So these two papers listed here studied the flipped threat model, where the BGP route is legitimate while the RPK is at fault. So in these papers, they studied that misbehaving authority can unilaterally take down the descendants' valid routes by adding or writing the ROAs by via revoking, deleting, or overwriting the RCs and the ROA objects in the RPK repository. So there are some real-world case studies. So the root cause of this problem is that an entity in the hierarchy does not independently own its address space. Actually, the parent or the ancestor node in the hierarchy, they own the address space and only sub-allocate the address space to the children. So they have the privilege to manage the children's RCs and ROAs. So we want to ask, can we design a new trust infrastructure to solve those problems, and anybody can use, can independently own their address space? So these are our design goals. The top design goals include any organization like the ISP, content provider, enterprise, and university. Anyone can independently own its resources, including the IP addresses and the AS numbers. And the validity of resource ownership and the mapping only depends on the owner itself instead of any third party. There are also some second level goals, including preventing the address exhaustion, enforcing prefix aggregation, and enforcing the organization level traceability and admission control. So in this system, we will deal with IPv6 address allocation and IPv6 and v4 address transferring. Okay, let me introduce the system design. This is the first part for the address ownership. We use a decentralized ledger, or commonly known as a blockchain, for the consistent prefix ownership and prefix to AS mapping. This blockchain is run by the eligible organizations. I will talk about what are the eligible organizations later. But here in this figure, you can see that we have an example. 4 nodes on the figure run the distributed ledger, including SP-A, SP-B, content provider C, and the university D. They are the eligible organization and run the blockchain. And every node will run a smart contract. We use the smart contract technology for to ensure the unique and aggregated prefix allocation. So the procedure is very simple. If ISP want to apply for a new IPv6 prefix, it just sends a request, which is a transaction asking for IPv6, for example, /32 prefix, and insert the annual fee into the transaction. Then send the transaction to the other node. The other node running the will run the smart contract to calculate the continuous prefix for B from the available address pool. Then write the transaction and as well as address ownership into the ledger. So today, at this point, SPB will be allocated a prefix, and then it can verify its ownership on the blockchain. So you can see that SPB doesn't apply for the address space from any third party. Instead, it just kind of digs or mines the prefix from the blockchain. Okay. So, but SPB doesn't own the address space forever. After, for example, if the prefix expires and the SPB doesn't renew the prefix, then the smart contract will be triggered and return the address prefix back to the pool. The second part of the system is the prefix to AS mapping. On top of the verifiable address ownership, the mapping is quite easy. Address owner can just initiate an ROA as a transaction and send to the ledger. The other nodes running the smart contract will verify the address owner, verify that the sender is actually the address owner, then writes the ROA into the ledger. And third step is on the routing plane. The relying parties can get the updated ROAs from the ledger and synchronize to the BGP routers, which then verify the BGP routes to detect the hijack problems. So you can see that the routers the router do not have to change because they can still use the current interface to the relying parties. So the change is only on the manage or the trust plane. The third part of the system is preventing address exhaustion. IPv6 has a very large address space, but it's still finite. So we want to prevent any party from exhausting the address space. We have 2 methods to prevent that. The first one is at the end site. It is also the practice today. The end sites, which are usually small networks, can get smaller address space, such as /48. And ISPs, they can get larger address space. For example, it can they can get /32. But if they want to apply for a new /32, they have to prove that the host density ratio of the existing prefix is over a threshold. So there are equation here to calculate the HD ratio, but basically it is a utilization rate of the existing prefix. Okay, if they have a very high, they have their HD ratio is over a threshold, they are eligible to request for a new /32. Okay. The second method we can prevent the address exhaustion is using money. Currently the IR annual fee for /32 is around from $1,000 to $2,500, and /48 is from $100 to $800. But if let's assume that we use $2,000 as an annual fee for /32, then consuming the whole IPv6 address space will cost 10% of the whole world GDP. So we think the attack is impractical. We know that the IPv6 not the entire address space is unicast. But if you consider that the longer prefixes are more expensive, and 32 requires some HD ratio threshold, then we believe that the combination of the two methods can prevent the prevent address exhaustion attack. The fourth part of the system is prefix aggregation. We want the entity to apply for the continuous address space, not the fragmented ones. So you can see that in our system, you cannot decide which prefix you get. You can only specify how large space you want, and the smart contract will calculate a continuous address prefix for you for the address aggregation. And the smart contract will run the sparse delegation algorithm, which is also currently used by the IRs. The fifth part is the admission control. So for the purpose of security and traceability, we think that only the organizations authorized by the IRs, NIRs, or LIRs are eligible to the router. And their identity information should be registered for accountability and traceability, just like today's WHOIS database. So to this end, we use the permission ledger. Only the entities whose identities are endorsed by the IRs, for example, the IRs and NIRs, are permitted to the chain. You can see that we still have the IRs in our system, but it is difficult. It is different than today, because in our system, the IRs are only the endorsers. You can see that we separate two functionalities in our system. One is endorsement, the other is address allocation. So in our system, the IRs, they do not own or control and manage the resource. They just endorsers. And besides that, in our system, the IRs and NIRs are just equal and independent. They do not have such as a top-down relationship from each other. Okay, we are still working on some open questions. The first one is the interdependency between the blockchain and the BGP. The decentralizer, we want to use the blockchain to secure BGP, but we should depend on the BGP to secure the blockchain. So it is a interdependency. We are working on that. But we think that RPK has a similar problem. The second open question is about the consensus algorithm. Currently, we are implementing permissioned Ethereum, which supports POW and POS, but eventually we think we are going to implement a new best consensus algorithm for our specific application. So ICP may be a candidate. The last question is how to get started. We want to request for /20 IPv6 address space to do the experiment. And so that the solution, we want to use actually we want to use a new /20, which is not used by the current IRs, so that they will not conflict with the current RPKI system. And then we also request that after the real world experiment, the address used in our experiment should be also still usable in the real product network. Okay, thank you. And we are going to write draft and open the code and run the experiment. Welcome to join us. Thank you.
Thanks a lot, Bingyang. So we are almost out of time, so please keep your questions really short if you can.
Oh, I'm sorry. Hi, Brian Trammell. Okay, very short. Same question from the last question that I asked when I was up here. Actually, can you go back to your open questions? I'm going to leave all of the venue problems out. You have a missing open question with respect to, you're basically trying to build a smart contract system that will more or less, for the address policy allocation, replace the policy development process of the various RIRs. Have you done an analysis of the policy development process and the outputs of that process to verify that you can actually model those in the smart contract, right? Like, so there's a lot of complexity there that's there for, you know, various historical reasons, but most of that complexity that's currently in those policies is there for actual reasons. So streamlining that out is not a feature.
Yeah, thank you very much for the question. Actually, we investigated the policies of IRs. They are very complex, but in practice, not all those policies can be applied in practice.
I would strongly suggest that you take this to the address policy working groups of the RIRs and get feedback from them on this. Because, like, I mean, streamlining the corner cases out here is really not a feature. Those are there for a reason.
Thank you.
Sort of related point that I think that, you know, a big open question is, you know, how much of these subjective, like, decision in address allocation, like, can be put into a smart contract. And it would be fantastic is if you could kind of layer this on top of, like, the Del map work, such that—
What map? Sorry?
The Del map work.
Okay.
That was presented earlier today, the delegated mappings, because then you could sort of have a side-by-side apples-to-apples comparison of how much do we gain. You know, obviously we gain by giving ownership of stuff. So the counterexamples you had at the beginning, those bad kinds of things can't happen. Like, you can't have something revoked by the authority when someone thought they had IP addresses. But you want to know how much additional benefit do we get by actually putting the allocation policy into a smart contract, as opposed to having it be done subjectively by people who can consider multiple things. And one particular problem that I anticipate is that it's going to be very difficult to determine the density of the use of the address space, right? And you can do things like probe the network, but the problem is you can't then feed that into a consensus protocol, because even if you have honest nodes executing consensus protocol, they might probe the IP address space and come up with different results, and therefore kind of get deadlocked.
Okay, thank you very much for your question. I'll give you the quick answers. The first one is about the delegation chain. What we think is different from their solution, because we do not want the delegation chain, because if you want the delegation chain, you depend on others to give you the resource. So we do not want that in this system. The second question
Well,
is—
the others could be, you could plug your allocation scheme into their thing, where instead of a single authority, it would be the output of some other process determining that this is a valid delegation. But it would be nice to make them work together such that you can sort of compare apples to apples.
Okay, yeah, I will think about it. Thank you. The second question is about, you said about probing the network for the HD ratio. However, in this case, we just calculated the assignment. I mean, I didn't introduce it, but the assignment is also logged on the ledger, so that we can use the assignment to evaluate the HD ratio just inside the system. It is a closed system.
Oh, are you saying even the sub-delegation cost? So if I get
the PA address delegation.
And I don't get that money. So if I have a /32 and I allocate a bunch of /48s, $100 to $800 are just burned. They don't come back to me to compensate me.
The money thing we haven't thought about the PA.
Because if I get it back, then I can just create a bunch of fake delegations, because it's not costing me anything. A bunch of fake people are paying me a fake $800, so I can just pay myself $800.
Okay, I will think about it.
Alyssa Cooper, I was going to ask you about the money as well, but if that's an area of unclarity, maybe that is moot. Just because here on this slide, it sort of indicates who would receive it. But then on the next slide, you have it looking more like it would be the RIRs. So that seems like an area where some more clarity would be useful. My other comment is just because there's been a little bit of confusion lately out there in the world about how address blocks can be assigned for experiments lately. That's a process that requires IETF review. So just wanted to make a note of that so everyone's aware. It can't go through the IRTF. It's a registry that requires IETF review.
Yeah, especially if you are considering that the IRs, 5 IRs actually send the 0/0, the total space. So we want an unsigned address space.
Yeah, that's according to the registration policy is an IETF review.
Yeah. Thank you very much.
That's a good point. Okay, great. Thanks.
Thank you.
Okay, so we were almost out of time, but we still want to give you a quick update what's happened to the Dinrg charter and our future plans. So I'm not going to read the charter to you right now, obviously, but so we had this discussion on the mailing list, and thanks to everyone who provided comments. So today we had to be quite selective. We couldn't really, have all the offered presentation on the program, so apologize for that. But we wanted to give you, say, some impression of what we think could be a good mix for future work in this group. So, protocol work, application work, systems, and also some ideas for, IETF impact in the future. So we are actually quite happy with that. We would like to get more feedback from you, what you think. So we talked a bit to Alison, the IETF chair, and I think we are in a pretty good shape with the charter. You can always optimize it. We will kind of fix some nits. But from our perspective, I think we're at a point where we could say we can go ahead, and we have some time to discuss this now at length. But so please get back to us or on the mailing list if you have views on this. Thank you very much. And we will probably have more time at the next meeting, so we will make sure. Thanks.